Okay, please have your.
Thank you, Professor. My name is Jinsoo Park. Actually, I'm not a professor. I just retired from the heavy industries 2 years ago. And from last January, I was here to help cooperate between Hyundai Heavy Industry Group and KAIST in all engineering departments. So I'm very pleased to meet you and share my experience with you. I was told today's topic is hull strength. So as I know, you are not familiar with ship industries, so I'm not going to deal with the subject in detail, but I'll try to give you some overall understanding about this topic. Before we get into the subject, here is just simple soda can, Coca-Cola. The left one is opened, an empty can. This aluminum can is usually made of aluminum 2.28 millimeter, very thin. So this opened can withstand about 55 kilograms. So my question is, this unopened case, how much weight can this soda can hold? So let's see. How much more? Can you guess? How much more? 500? Oh, I think too big. How about you? Sorry? 200? Oh, yeah. I think between 200 and 500. Let's see.
In aluminum can, by soda can, or space rocket, it's going to be much stronger when there is some pressure inside. So I'm going to say that it's going to be at least twice as strong with the soda.
He guessed maybe twice.
So here we go.
So weight is being increased, and the current weight is being displayed on screen. Already 200. Whoa, yeah. 300. 330. So there is some.
It's going to go.
Oh, but yeah, finally, yeah. Can you see the difference between buckling mode of these two cans? Quite different because the soda and some pressure in it.
That was really nice. And let's see the result. 360 kilograms.
Yeah.
Way more.
It
that was really nice.
Resisted 360 kilograms.
Like really
About 5 to 6 persons, right? Only one person and 5 to 6. So let's think about ship. Here are some interesting pictures showing typical examples of entire loss of hull strength. So my question is, how big load should be to break this ship in two parts? How big wave? Wave height and wave length. can the ship withstand? What kind of wave loading or cargo loading to be considered in designing ships? So the main design purpose of hull strength is to guarantee safety in the lifetime. For example, about 20 years or something. That's the main purpose of hull strength. These kind of catastrophic damages may have been due to excessive wave loading, quite big buoyancy at center, something like that. Here are some types of ships. The ships are called, depending on the cargo, in some cases, bulk carrier, carrying grain or coal. And container ships, carrying containers. Tanker, crude oil or refined oil. Gas carrier, liquefied natural gas or liquefied propane gas. Car carrier, cruise and ferry. There are many types of ships. So as you see, very different types of ships. So we can imagine internal cargo loadings are very different depending on this cargo. The first ship looks like it's empty because the ship is fully loaded. The ship sinks down to this red line like this one. So this one is fully loaded. This one is empty. We can see. Ship and hull. So basically, ship may be defined as a large watercraft traveling the oceans and some deep waterways and carrying goods in support of specialized missions. So when we talk about hull, it refers to main structural part of ship. Let's see here. Ship is composed of many components, so cargo holds, bow, and engine room, superstructure, and rudder and propeller. So when we say hull is referring to usually the main structural part of cargo hold, except deckhouse, rudder, and propeller. So the basic hull design concept is to optimize the structure considering low cost and strong enough. This slide shows at the moment, the largest container ship. Its length is 400 meters. This largest container ship carries about 21,000 containers. TEU indicates right here 20-foot equivalent unit. This size containers. So the number of the containers is about 21,000. So, but currently we are designing more than this one, but 22,000 or some more. Yeah. So the container ship is being bigger and bigger. This slide shows a part of hull. Hull may be defined as watertight body of ship. As I said before, main structural part, including cargo hold, and holding many kinds of cargo, withstand external and internal loadings. maybe top part, upper deck, usually partially open to handle the cargo. This one shows the typical mid part of the ship hull of tanker. This structure mostly welded joint, and this midship section very similar along the length from here to the deck house. So hull strength design of midship is the main thing to design hull. So as you see from this figure, the structure is very complicated. Upper deck, bottom shell, side shell, longitudinal bulkhead, something like that, very complicated. Here is a brief description of shipbuilding process, which is divided by contract, design and construction, ship trial, and delivery. Usually it takes about 18 months up to whole delivery from contract. Construction starts from steel cutting. Steel cutting usually in indoor factory, and block fabrication and block assembly is being done usually in dock. And commissioning and outfitting usually at keyword on the water by the ground. The sea trial is usually very near from the shipyard. So when we design hull structure, our purpose is to make the ship structurally safer and functional in the lifetime, about 20 years, considering maximum wave loading, repeated small wave loading, and various kinds of cargo loading, as you saw in the previous slide. And sometimes we need to evaluate accidental loading, such as slamming, collision, etc. So our purpose is to design the ship for cracks, buckling, and fracture not to occur in this ship lifetime. There are many types of wave loadings in the ocean. A ship, we may say, A ship usually encounters about 10 to the 8th wave loads in the period of 20 years. Here are very various waves from small wavelengths up to these very large wavelengths. Among these waves, the maximum or the worst wave bending loading occurs when the length of wave is the same of the length of ship, like this one. Because in this load case, ship is subject to be bent very large. So, and then these irregular waves are usually encountered in operation. So cyclic loading is applied by repeatedly and finally causing to fatigue cracks. Here are some description of maximum bending moment for sagging case. When we calculate the maximum total moment, then we have to sum a maximum static moment and maximum dynamic moment. In this figure, even in the still water condition, bending moment can occur because of the cargo distribution like this. The center hold is full, then the other hold is empty, then structure is bent. This hogging, this sagging deformation. And this under this wave, the wavelength and ship length is the same, then the largest wave bending moment. So the maximum is these two bending case coupled. That's the design wave loading, the design bending moment. Yes. Oh. Wavelength can be 400 meters. Yeah. Yeah. Ship length is 400. Yeah. So wavelength can be longer than that. Like so. Let's see. Ship is 400 meters long. The waves can maybe longer than that, shorter than that, right? But among all of those waves, in the same case is the worst case, what I meant. Oh, here are some pictures and rough seas that ships can encounter during operation. So her structure should be designed to withstand these kind of various severe loading conditions. Excuse me. So ultimate loading such as bow impact coming from ahead. And this one is bottom slamming, very severe wave loading, something like that. So when we design the ship, especially hull structure, then we have to consider these rough sea storm conditions also. In the designing ships, we are concerned about the weakest point, which is usually a midship area, top and usually bottom. So let's see, the ship is undergoing this kind of wave, then ship is deformed by hogging shape. The upper deck receives tension force, bottom is compression force. So maybe cracks happen in this area. And on the bottom, buckling may happen. So if structural failure, crack initiation, and subsequent growth and final fracture like this one should be avoided by proper design of hull structure. So we need to consider very deeply in determine the quite proper thickness and arrangement of structural elements. Cracks is the most frequent structural damages, which is simply defined as separation of material. Cracks may occur at stress concentration areas on the deck or bottom, at bracket toes, and some around the opening, something like that. If the crack happens, then it keeps growing until some length. About this figure shows about 20-meter long crack grows, and finally it breaks down. Buckling is another form of failure frequently occurred in ship structure, which is simply defined as structural instability, such as a large lateral deformation of panel or stiffener under compression loading. In this loading condition, bottom undergoes compressive loading, and it may be subject to buckling. So it may cause to final whole ship collapse like this one. So buckling is very dangerous phenomenon in ship structures. This figure shows bottom shell buckling test. So when you design hull structure, two important things is to fatigue cracks and buckling. So those two are the most important subject for design. I'd like to talk about section of ship. Rigidity of structural section usually depends on the shape of section, even with the same sectional area. Let's see these four kinds of section. Sectional area are the same, we are assuming. Then the first one is very strong to vertical, but weak to lateral. Second one is weak to vertical. Usually this closed section very effective for vertical, lateral, and torsional movements. So basic concept of ship section is make the ship section closed one. So let's see this typical section of ship. The whole part is closed, and another closed section is three closed section in it. So more cross section there is, the structural section is more stronger. Here are some various sections of ships. The left one is oil tanker, whole closed section, and two small closed section. In the car carrier, many decks inside and many closed section. Bulk carrier, even though there are some opening on the deck, but opening should be smaller is possible, but a large closed section in two closed section, LNG carrier and container ship. In container ship, we need to large opening to carry a number of containers, but considering this weakness, the small closed section we make on the whole section to compensate the sectional rigidity. let's talk about the strength of material. I'm not sure how much you are familiar with this one, but I want to just remember what stress is. Stress is the most important index to evaluate the safety of structure. Basically, stress is defined force, applied force divided by area. And the strain is elongation divided by length. So stress and strain are related by constant E, which is Young's modulus, but it measure of stiffness. So E is larger, then the material is stronger. So this figures the relation of stress and strain. Under yield, it shows linear relation. This right one video shows the behavior of material is linear and yielding starts and final fracture. So in order to evaluate the structural performance, we need to obtain the material data of steels used in the hull structure. Usually when we design the ship, stress must be lower than yield stress. For example, 90% of yield stress. Some point about this one. Yeah. Stress, we can say, a measure of the internal resistance in a material to externally applied load. So, as I said in the previous slides, stress defined force by cross-sectional area. So in the design of ship structure, it's very not easy to handle force because wave loading and cargo loading is almost fixed. So we make the stress under the allowable limit, then we need to make the cross-sectional very safe. So that's why we design the whole structure, a very complicated section. Your stress and stress relation is given by this one. So E is Young's modulus. Let's compare two materials, steel and aluminum. Steel is mostly used in ships. Steel is about 3 times aluminum, stiff and stronger. Simple beam theory may have covered in the previous lecture. So just let's talk about this formulation. Stress is given by moment divided by section modulus. This is very simple, but this simple beam theory is applied to design very complicated ship section. For example, let's see about this simple cantilever beam. Force F, then moment M is given by F times L. And the section, if the section is rectangular, then this section modulus is simply given by BD squared divided 6. Very simple. But this simple theory is applied to ship structure. Bending moment is calculated by wave and cargo loading. Then this section modulus should be calculated or determined, considering this very complicated section. So when we designing hull, main target is to determine Z, the section modulus, so that the resulting stress is lower than the allowable limit, about 90% of yield stress, something like that. So what I mean is very simple theory is being used for designing complicated ship structure. Here are some figures indicating stress and design. So we usually do many kinds of structural analysis to calculate stress and deformation at every point of hull to optimize hull design, considering plate thickness, stiffener size and arrangement, cargo distribution, sailing route, considering wave data and loading, and ship speed. All of these are the most important factors we need to consider. Here are some examples of structural failure, many kinds of fatigue crack or ultimate cracks. This one, cracks may have happened at upper deck and grew to final fracture. This one is at upper deck, longitudinal stiffener toe. This one is buckling happened at side shell plate. Anyway, these are the typical failure shape of hull structure. Weight and buoyancy. Usually when ship is floating on water, it means total ship weight is the same as buoyancy. So it becomes vertical equivalence. But weight or buoyancy changes, then ship moves to make another vertical equivalence. Actually, wave height continuously changes, so that's why ship continuously moves. There are main design loadings which can be categorized like this one. Hull girder loading, vertical, horizontal bending moments, torsional moment, shear force. Or impact loading like bow flare impact, bottom slamming, collision, explosion. And cargo loadings, various kinds of goods, and vibration and temperature is special loadings. I found a very interesting video which shows very effectively what these loadings are. Let's see.
A simple understanding of the strength and forces acting on a ship's structure is also important. An optimal ship structure has the minimum amount of steel to provide the strength and stiffness necessary to withstand the full range of internal and external forces exerted on it from sources such as the light ship weight, the weight of cargo, ballast, fuel, etc. And of course the harsh sea, the marine environment, the movement of the ship, and vibration. The hull may be compared to a simple beam. When a force acts on the beam, it bends and stretches in accordance with the magnitude of the force and the strength of the beam. Loads generate vertical static forces in still water. Waves generate dynamic forces that act vertically, horizontally, and transversely, also creating shear and bending forces, in addition to tension and compression. Longitudinal forces will be experienced from the bow due to a head sea. So at sea, the ship's hull is continuously being exposed to a large number of forces coming from practically all directions. The same simple beam principle also occurs in complex combinations inside the ship's structure, where plating, frame, stiffening, panels and brackets are built up from many separate small beam elements, all working together. Due to the many and variable forces acting upon them, these elements may partly fail and develop cracks and damage in critical areas, causing a serious reduction in local and overall strength. In addition, aggressive corrosion that is found when placing steel in the marine environment ruthlessly weakens the steel and its welded connection.
Yeah, very useful video, isn't it? So let's see more about these loadings one by one. Although the bending moment vertically happens, as I said, even in the still water condition, depending on the cargo distribution, bending moment can occur. In this case, the center part goes down. In this case, center part, if empty, then the hogging shape may be happening. As I said before, if wavelength is the same as the ship, then the largest bending moment, these two cases, compression and bending, cyclic tensile and compression stresses occur at deck and bottom. These are the deformed shape of the hull structure. So vertical bending moment, I think the most important loading condition when we design hull structure. Most important. Yeah. The second one is horizontal hull bending moment. When waves come from side like this one, then ship moves sidely, shows very large rolling motion. It causes a very large horizontal or lateral bending moment. Why is it important? Because this horizontal bending moment is coupled with a vertical bending moment, and it makes the stress at upper deck corner very high. So this condition is very important when vertical bending moment is coupled together. Sometimes it causes capsizing or loss of stability. This is one of the loading conditions we need to consider in design hull. The third one is the torsional moment. This happens when ship encounters waves coming from this direction, 45 degree. In this case, the water depth difference happens right and left. So the difference of wave water height makes the ship twisted and different direction at fore and rear. So torsional moment is applied in this case. So this kind of loading is very critical to container ship, which has very large opening along the deck. So this one is very important loading condition for container ships. Next one is bow flare impact. In ship structure, this part above the water is called bow flare. So bow flare sometimes subject to wave loading under the wave direction of 0 to 45 degree in this direction. Then a very high impact loading may occur on this area. Sometimes it causing a permanent yielding damage So it's very important for head sea condition. You can imagine what pressure is in this area. Very high pressure can happen at this flare. Another impact loading is bottom slamming. It also happens in head seas, usually very high speed ship. If ship goes on this shape, wave profile, then the motion moves up and down very large. So when it descending down to the water, very high impact loading happens at this bottom. Sometimes it causes very large severe structural damages. So it's another type of very important loading condition. Maybe can you see some movement of ships under the head sea condition? Next one, almost. Next one is collision. The collision is, I must say, is important for tanker or gas carrier because if this kind of collision happens, spillage of cargo happens. So when you design tanker and gas carrier, we need to evaluate side structural strength for the collision like this one. So if another ship hits the side, then we hope, even though side skin fracture, that inside skin inside should not be fractured to prevent spillage of cargo. So collision analysis is often carried out in design. Here is picture shows some spillage of oil in actual ship collision. Another topic is ship structural response to explosion, especially warship. In warship, sometimes it undergo explosion just below the ship or near the ship. So this explosive loading, the structure of the warship resists some kind of loading. So to evaluate this response, we sometimes use technology so-called FSI, fluid structural interaction, where a ship is modeled like this. And also water, seawater around the ship is also included in modeling, considering explosive. Oh, finally, yeah. This is the last one. The shipbuilding industry in Korea is very big. Currently, world top number 1, 2, 5 are Korean shipbuilders. Hyundai, Heavy Industry Group, and Daewoo Shipbuilding, and Samsung. The ranking is based on the residual value of attained contract, the number of ships left to be constructed. So in Korea, shipbuilding industry is good business to get into in your career, I think. In automobile industry, Hyundai Korea company is just 5 or 6. Finally, thank you for your attention. Yeah.